some of you cannot make today. Okay, so let me repeat here. So please refer to the video of the lecture, our lecture, and our experiment videos. Okay, so that should be correct information. Some of the information on the handout might not be up to date. Okay, feel free to ask me if you have some questions. Okay, but I think refer to the video. Okay, both either lecture or the video experiment for the correct information. Okay. Number 4, lab number 4, next week, we will start working on the pump experiments. Okay. We're done with the open channel, that water machine. Okay. Not too much fun. Okay. We're done with it, right? We verified a couple of theory, momentum, conservation energy, conservation mass, those kind of things, right? All 3 of the conservation law has been verified, okay, has been experimented. Okay, so I think we're done with that equipment. So we will start working on the pump. Pump is important. Pump is to me, is the most important topic. Pump and the piping all together, right? It's not just pump, always pump, it's inside a piping system. So pump with piping, that's, to me, it's the most important topic, fluid mechanics topics, okay, for you, for our program here. If you work in the local industry, it's a petrochemical industry. We usually, anything related to the fluids is like either piping, pump, or compressor. Okay, so pump and piping is really important. Compressor is a topic for the compressible fluid, right? So it's out of the scope of ENGR312, right? Dr. Chandra had what? Gas dynamics or thermal, two thermals, right? And the gas dynamics that talk about the compressor, I guess. But for the incompressible fluid, it's all about the piping and the pump. It's really important to you. Okay. In the fluids class, we probably have plenty of times talking about the pipe flows, right? But I guess we didn't have enough time to talk about pump. We probably mentioned the pump head, those kind of things briefly, but not in depth. Here, let's try to talk a little detail about the pump. Okay, those pump curves, system curve, affinity laws, pumping parallel, pumping series, MPSH. Okay, these are all the common terminologies when you talk about pumps. At least you need to know what are they and how to obtain those curves, how to measure those curves. Okay, so that's the scope. Okay, the purpose of the upcoming 2 or 3 labs. Okay, maybe 3, 4 labs, including maybe a piping measurement. Okay. Some announcement here. The news is I have one more experiment video only. Okay. Unfortunately, I was informed by end of February, it's possible that we can access Juhol or ETL, something like that. But I think that it doesn't happen. Now it's March 3rd, okay? They still ask us to wait, okay? So as soon as I can access ETL, I know the pump is there. I can shoot more videos, okay? But hey, they don't allow me to go there. So that's the situation right now. I have one more video, okay, to go. But after that, I need to find some way, maybe tell you more detail about the experiment instead of actually showing the experiment, something like that. Okay, so we can still do the calculation, do the reporting. Okay, so that's the plan. So hopefully in 1 or 2 weeks, we will be able to access the building. Then I can make more videos and that would be better. But I'm not sure when exactly the time. Okay, so I think they have to do even they fixed everything, they have to go through the inspection. Okay, fire inspection, all those kind of inspections. They need to make appointment, they take time. I don't know how long it will be. So that's the situation. Okay, but I find a way. For you. We can still do some lab. Okay, so although we may not be able to do it as we planned. Okay. Okay. So let's talk about pump. Let me share my screen. Can you see it?
Now we can see it.
Okay, great.
It's a white screen.
White screen, yes, yes, yes. So pump, it's a typical layout. Let's just draw a typical layout since we're going to talk about the system curve later. Right? This is a typical situation. Okay, so usually the purpose of the pump is to drive the flow, deliver the flow from a low place to a higher place. There are two purposes, right? One is to deliver from a low place to a high place. The other is to make flow. Okay, to make speed, velocity of the flow. So basically, there's two purposes. So in different applications, you sometimes more towards deliver fluid to a higher location. Sometimes some application is more towards generating a faster speed. Okay, so but for this you have a system equation, right? System that's the Bernoulli we learned from the fluid mechanics. So you have elevation Z1, you have elevation Z2. Okay, so that's the speed, right, inside the piping system. So the pump drive the flow. Okay, so the first thing I think I want you to know is that the suction and the discharge of the pump. This is the pump, right? This is called suction, right? Suction. This side is discharge. I always hear people say that, hey, I put a big pump, you have a big discharge, you have faster flow than the suction. No, conservation of mass, always, no matter what, okay? The suction speed is equals to the discharge speed. Suction flow rate equals the discharge flow rate. They are always the same, conservation of mass. So you increase the discharge, you have to suck more fluid into the pump. So it will always be equilibrium, okay? Always the same. Okay, that's very important to know. So you have only one flow rate inside the system. So for the entire system, just like we did in fluids, right? 1 and 2, the two ending points. So between 1 and 2, the entire system can be characterized by that Bernoulli equation. So-called actually the energy equation in the piping system. Well, but everybody in industry just call it Bernoulli equation. So it's actually not, but it's fine. So I think everybody should be very familiar with this equation. If you're not, this is the time to remember it. Okay. Okay. So pressure head, it's kind of like energy, right? Energy conserved. Okay. So one is before the system, two is after the system. It will be conserved. So P over gamma is the pressure head. We call it the pressure head. Okay, in the industry, the convention, let's just use a head. It's more often to use head in the industry than in the use of pressure. Okay, so pressure head is the first term. Z1 is what? The elevation head, right? So V1 square over 2G, that's called velocity head, right? At the location 1, right? Velocity head, V square over 2G. Okay, HP is the pump head, okay? And also at the end, you have pressure head, elevation head. Elevation head will be higher, right? Because some of the energy you deliver to the higher location, right? So elevation head, and then at the end, the velocity head, then you have losses for the entire piping system. Okay, so HL is the loss. So based on this equation, you should be able to calculate the pump head required to drive the system to make it work. Okay, is that right, everybody? Okay, that's one of the tasks, one of the experiments we're gonna do. You're going to measure the system curve. Okay, then you compare to the theoretical calculation of the system curve, which is just this equation. This equation, you can use it to calculate the system curve. Let me show you what the system curve look like. Okay, before I do that, let's rewrite the equation. Okay, so something zero, right? A lot of zeros in this equation. Anybody can help me? Zeros? Let's pick the zeros.
The pressures are both zero because it's open atmosphere.
Yeah, open atmosphere. Most of the application industry here is open atmosphere here. Okay, so both P1, P2, zero. Anything else?
Z1 should be zero.
Let's not to make Z1 zero. You can, but it's not really common to you put zero. Usually people put in the datum as zero Z, where the pump is. They put this as a usually, okay, by convention, okay. Yes, you can put Z1 zero Z, but then your pump become a negative Z, okay? So it's not very convenient for you to do the calculation. Let's make it all possible or positive. That will be better, okay? Good, at least you're thinking about this, that's good. But let's say Z1, Z2 not zero, that positive. Who said the V?
Oh, V1.
V1, right, you said V1?
Mm-hmm.
Yeah, both V's are zero because these are tanks. Storage tanks, it's very big, right? Surface, you don't have a water velocity on the surface. So let's just assume it's zero, okay? Although it changes slightly up and down, but that's not comparable to the speed inside the pipe. So let's neglect that for the simplicity of the calculation. So your pump head actually, required pump head for this system equals Z2 minus Z1 plus HL. Okay, it's kind of easy now. It seems like, Z2 minus Z1, they call it a static head. Okay, we'll learn some terminologies here. It's a head, right? Z is a head. So if people talk about a static head, that means the elevation difference between the starting point and ending point. So basically, your pump head need to overcome. Even you have a lossless system, the pump head has to be large enough to overcome the elevation difference. Right? That makes sense? So the static head, definitely the pump head need to overcome. Okay. So if you want to rewrite it, the loss, you know what loss look like, right? You had fluids, right? What is the equation for the loss? Anybody? These are the equations I think you really need to memorize. It's good for you, okay? So for your future work, like a loss, frictional head loss, what does it look like? If you cannot spit it out the equation, then that looks bad to your boss. Okay, so what does the friction head loss look like? Anybody? So if you don't remember, that's fine. This is the time for you to review it and try to remember. Okay. Anybody can help me out here?
It's like FL something, possibly.
Yeah, that's right. You remember 2 letters here. Out of like 5 letters. Okay, what else? What else? Think about it. I'll help you memorize it. What else dictate the loss? Think about pipe flow. Length, sure, length dictates the loss. The longer it goes, the more loss it has, right? Okay, what else?
Does it have anything to do with like different pipes? Like, let's say there's a turn in the pipe, a different pipe would have a different number.
Of course, we will talk about this later. These are the fittings, minor loss, elbows, those kind of things, right? I'm talking about the frictional head loss, okay? Just friction, by friction, it's not by the shape. But you still need to remember this basic fundamental equations. It's good for you, really good for you, okay? Length. Length has an effect on the loss. What else?
Velocity.
Velocity, yeah. Velocity has the effect on loss, right? So let me ask you this. Is velocity and the loss proportional? Is it the larger velocity, you have more loss, or vice versa?
I think that should be the proportional.
Proportional. Everybody agree? Is velocity is the larger the velocity is, the more loss you will have. Is that a common sense to you? Okay. Yeah, it is. Dinesh is right. Okay, the velocity is proportional to the loss. So the next question is, so if it's proportional to the loss, the velocity should be on the numerator or should be on the denominator of this equation?
Should be on the numerator.
Has to be on the numerator. Okay. So V is there. Okay. So it's V or V squared? This probably you need to remember. It's V squared. Okay. On the numerator. Okay. So what's on the denominator? What other factors affect the piping loss?
The value of G.
What? The G. Okay. G, right? G is a constant. 2G, V squared over 2G, right? You should memorize it. We already have that term in the equation. V squared always over 2G. Okay. Good. One more.
Isn't there a K constant for
No,
like?
it's not. It's not.
Okay.
That's the minor loss and the fitting. We haven't reached that yet.
The
This is-
diameter of the pipe.
Exactly. Diameter is the last factor, right? That's the bigger factor. Is the bigger diameter the bigger loss or vice versa? If you buy a pump, you want to buy a bigger pump or you want to buy a small pump? Oh, I'm sorry. If you buy a pipe, you want to buy a small pipe or you want to buy a bigger diameter pipe?
Bigger pipe would be
Bigger pipe.
smaller loss, right?
That's right. So it's inversely proportional to the loss, right? Diameter is the bigger the better. Okay. So where's the D go? Is numerator or denominator?
Denominator.
Denominator. See, if you can remember all the factors, then you remember this equation. Okay. Okay. Really, as an engineer, if you deal with fluid topic tasks, you really need to remember this. Okay. Frictional hair loss. This is okay. So, okay. What else? Then as a minor loss, you talk about the fittings, elbows, valves. So this is characterized as the minor losses. Okay. Even entrance, exit, everything on the pump, a flow meter, everything on the piping will contribute to a little bit loss. It won't gain, it always lose, right? So everything on there will contribute to a little loss. So in that sense, we don't have a theoretical equation like this to calculate the minor losses. So we'll have to do some empirical experiment measurement, to get those loss coefficients. So in that sense, all the minor losses will be grouped together as case. All kinds of information, all kinds of different components will have a different case. Of course, it's still related to the velocity head. Okay, so this is the minor loss terms. That make sense, everybody? Okay, I hope you attended the class, spend an hour here, chat with me, and hope you learn something. It's not wasting an hour time. Okay. Time is precious, right? Priceless. So try to learn it. Remember it. It's easy to remember. Okay. The losses are V squared over 2G. Then times the coefficient. Okay. So minor losses we have K. So you need to have the engineering table, handbook or whatever table. Fluids textbook has the table for all the case, for all the components, right? For the valve, different valves, gate valve, ball valve, whatever, and elbows and the bands. Each of them will have a K value. Okay, you can use. So in your system, if you have for example, you have an elbow here. Okay, so based on the diameter, you should be able to find a K value for the elbow to represent the losses from the elbow. You have a valve, sure, you will have the K for the valves. Okay, so I have a summation sign depending on how many components on the every one you have to the K, and you have to account for it for the loss. Okay, to the system. So this is your system curve equation. Okay, this equation, your pump head required is really, really, really related, dictated by the flow rate. Okay, in pump curve, always Q, flow rate down there. But in your equation, you have velocity in there. But velocity and the Q basically is same thing, right? Okay, you can convert. Now you should be, after 3 labs here, you deal with a lot of flow rate, velocity. You should know how to convert the velocity into flow rate. Right? Is that right, everybody? Okay. So what does the curve look like? Okay, so look at this. The first term has no velocity. So in case, well, for the extreme case, let's say your velocity is really small, almost 0. Let's say velocity is 0. What's the pump required? You know, it cannot be absolute 0. If there's no flow, then why you need a pump, right? But let's say you have infinitely small velocity. Let's say, assume velocity is close to 0. So at the beginning, when flow rate is 0, you need a little bit pump head. Your pump head is basically to overcome the static head, the elevation difference between the beginning and the end, right? That's the point. So this is Z2 minus Z1. This is delta Z at the beginning, okay? Then the curve go up and go down. So velocity is a numerator. So when velocity increases as the horizontal axis goes, your required pump head will increase. Is that right? Look at the equation. Okay, you're going to be an engineer soon. Get used to reading equations, from looking at the equation to tell what the physics is, what the reality is. Okay, that's the difference between an engineer and a regular handy person, right? engineer always has to be handy, but you're one level above. Is you play with equations, you deal with equations, you're comfortable with equations. Okay, so with this, the curve, the system curve should look like this. Is that right? When velocity increases, see velocity in the numerator. The rest of them are all coefficients, right? Only velocity changes. So when velocity increases, so your system need a higher pump head to drive the flow. The flow is actually, those velocity terms is from the losses. Okay, you need to overcome the pump head needed to overcome the static head elevation difference, as well as it need to overcome the losses in the system. Okay, so that's the fundamental background of the system curve here. So far so good, everybody? Okay, so this is really serve a purpose of the review, right? Okay, I really like you guys to have a good, although we only have one fluids class. For civil engineering student, you don't even have one whole fluids class. You have, are you doing like a thermal fluids, half of the thermal heat transfer, half of fluids, something like that, right? Okay, so here's a review, okay. So this is a system curve. This describes the system. That has nothing to do with your pump. Notice, so far I never talk about what type of pump is, what's the performance of the pump, nothing. Okay, it's just this equation, this curve just tell you that if I want to make this thing happen, deliver this water from low to high, deliver this fluid from lower tank to the higher tank. If I want it happen, I need that much head from the pump. So based on this, maybe I can go find a pump to satisfy this condition. Okay, this is for you to understand your system. Okay, but what the pump curve look like? Okay, it's different story than pump. So if you go to buy a pump, the manufacturer will supply you a pump curve. Okay, the pump curve is also pump head versus flow rate. Okay, that's why a lot of people confused about with the system curve and the pump curve. Okay, pump is, you know, performance curve of the pump belongs to pump. It look like this. Okay, see, this is a downward trend. For the, see, pump is a mechanical device. Okay, mechanical device just like your car. Okay, like a car, the performance it won't be like if you want it to have a faster flow, it will give you a faster pump head. No, pump head is just like for your truck, the towing power, right? If you want to tow a boat, okay, so that's a power you need. See, pump head is a power, right? So what do you do when you try to tow a boat? Do you want to drive 80 miles per hour with highest gear on your truck, or you want to lower your gear to 1 or 2, drive like 30 miles per hour? I guess most of you towed boat before, right? Here in Louisiana, come on, you're next to the water, right? So I guess that's the situation. So you cannot get both. You can't get the fast speed as well as the bigger towing power. Okay, for mechanical device, the performance is always like that. If you want to have a flow rate, if you want to have a faster flow rate, the pump can only provide you a little bit of the pump head. So you can, in other words, it can deliver to a lower location. Okay, if you want it to deliver very, very high location, you need a lot of power, then you have to sacrifice. You have to work with a lower flow rate. Okay, that's why the pump curves look like this. It's a mechanical device. It's nothing to do with your system. Please try to separate the pump curve and the system curve. Pump curve is for the pump performance. The system curve is nothing to do with your pump. It's just what the system required. Okay, so energy point of view, one system required is reasonable. If you having more flow to the having faster flow in the system, then you need a bigger pump, have larger pump head. Okay, but for the pump curve, it's opposite. It's just for a whatever pump, it can only work. If you want a faster flow rate, you have to sacrifice with a lower pump head. If you need a bigger pump head, then you have to run at a lower speed. Okay, so when you buy a pump, so they give you a pump curve. Okay, so you have your system curve. Either you measured, in your later we will know how to do the measurement, right? This is one of the lab we're going to do. Okay, either measure, or you can even just theoretically calculate it based on all the information you know. A lot of people in the capstone project, they need to calculate their system curve. They know every information. They have 52 valves, 35 elbows. For larger system, so you have to include everything, count it right, and put everything on information in the equation. Then you can actually calculate your theoretical system curve, right? Okay, so when you buy a pump, okay, now you have your system curve. Then you buy a pump, they give you a pump curve. Okay, so you put them together, like I did right now, right? It may have an intersection. Not necessary. Okay, if your pump curve is like this, no intersection with your system curve, what does that mean?
Pump can't do the job.
You can't do the job. See, everything, all the pump head is lower than the system required, and at any flow rate, it won't happen. That won't make the system work. Okay, if everything is above, that's too much also. Okay, in engineering design, it's really budget oriented, right? Everything you need to design, anything you have to think about the budget and the cost. Maybe if the pump curve is so high like this, maybe it work on your system, but cost too much. The pump head it gave you too much, right? A lot of electricity needed to make this big pump work. So in the long run, the operating cost will be huge. Then it's not good. You need to find something reasonable. Okay, something cost-wise is the most efficient. Okay, so then among these three pump one, let's say pump one, pump two, pump three. Okay, so you see pump one have an intersection with your system. So what does that mean?
It means that pump can achieve a very specific flow rate.
That's right. If this pump being placed into your system, it will run at this flow rate. At the same time, it will produce this pump head. See, how great is that? Pump selection 101. Okay, this is called operating point of this pump in your system. Okay, simply, that's why it's very important to have your system curve produced. Then, if you get the pump curve, put it on there to see where is the intersection. That's actually, without even having the system, you can theoretically predict what is the operating condition, what the flow rate it can produce, what the pump head it can produce. Okay, so this is basically pump selection 101. But this might not be what your boss wants. You know, this is 1,000 GPM, so maybe your boss wants a 1,500 GPM. Okay, so, well, this pump doesn't work. Go find another one. Usually your boss is not that strict. Give you a range. Maybe give you a range between 1,000 and 1,500. So you have a range to select and make sure, you know, within that range it's okay. Okay, so if your required range is not this point, not this flow rate, not this pump head, then you need to find another one. Okay, now you get a new operating point. Is this operating point good? Ask your boss, hey, it's good for me. Okay, you go ahead, buy this one. Okay, is that good, everybody? This is really how you select the pump. Okay, then the more information you want to look at is BEP, the best efficiency point. When the pump manufacturer give you the pump curve, there's a range. There's a range on the pump curve that the pump works with a best efficiency. Okay, you want your operating point located in that BEP range. Okay, of course, you want the best efficiency point when the pump runs. If the pump run not on the best efficiency point, then it will, you know, long run, it will damage quickly. Okay, you always want it to run on the best efficiency range. It's not a point. BEP is like a range. Okay, then outside that range, the pump, if pump run at too low a speed, then you maybe work for maybe a system. You can force it to run like this. You know, it's okay. The pump can run, but in the long run, it will damage quickly, and you have reliability issues maybe. Okay, so this is the pump selection process. Okay, basic selection process, but sometimes you need more details. Okay. Okay, is that good? This is the fundamental. So having said that, it's really, I think it's important for you to know how to produce a system curve and how to produce a pump curve. If you have a pump there, you should be able to measure the pump curve. Okay, these are very important informations. Our engineer deal with fluids topic should know how to measure the system. Okay, measure the system curve for the target system, and how to measure a pump curve. If you have a pump, you don't have the pump curve. Maybe it's old pump there, you lost the pump curve, you don't have the document anymore. You can simply measure it. Then you know the performance of that pump. Okay, so that's a goal. Okay, so for the first lab, not first lab, number 4, right? Number 4, I think it's designed to actually measure the pump curve. Okay, pump curve. So pump curve usually you will get from manufacturer, but what if you don't have it? You can measure it. Okay, so then the number 4 lab, you measure a single pump curve. Later we also measure the pumping parallel and pumping series pump curves. Okay, so now let's talk about the measurement. How to measure the pump curves. Okay, so me. So usually in a system like this, you have a couple of things. Okay, you have pressure gauges. Okay, if you go to look at any of the pump in working industry, there are always two pressure gauges, one before the pump, one after the pump. Is that right? Okay, I don't know any of you did the intern or working in the industry. Whatever pump is, that always come with a pressure gauge before it, in the suction pressure and the discharge pressure. Okay, you want to know, based on these two pressure value, you should be able to measure the pump head. Okay, pump curve is pump head versus Q, right? Is that right? So if you want to produce a pump curve, you need to know pump head. Okay, pump head is from pressure. Okay, Q is from what? There might be a flow meter. Flow meter somewhere downstream of in the discharge of the pump. Okay, there's only one flow meter needed, right? Usually, it's conservation mass. So suction flow rate should be the same as the discharge flow rate. So usually they put it in the discharge. That's because discharge, the flow is what we really want it to be, right? So they put the flow rate, flow meter on the discharge. Okay, so okay, this is the pressure gauge P1, P2, two pressure gauges and a flow meter. I said this is enough to measure a pump curve as well as a system curve. Think about how to do that. Any of you know how to do that? If you know, it's good. If you don't know, that's good for me. After the class, I make everybody know how to do it. Okay. How do you, first of all, question is, you need the flow rate is pretty easy. Look at, let me use another paper. Okay, you have two pressure readings. Which one has the bigger pressure, by the way? Educated guess. P1 high pressure or P2 high pressure?
P2.
P2, right? Because you have a pump. Pump is supply pressure to the system. Okay, P2 of course is greater than P1. Okay, so how do you convert? Your goal is here is pump head versus Q, right? It should be like this for the pump curve. Okay, so you have pressure readings. How to convert the pressure P1, P2 into the pump head? Usually those pressure gauges are really close to the pump, just immediately before and immediately after. Okay, so that you don't have to consider the pipe loss in between. Okay, no, let's say that no loss. Any loss in the pump, it belongs to the pump curve, so it doesn't matter. Okay. So, but how do you convert? Q is easy from the flow meter. This thing can read Q, right? It can give me a Q. Flow meter, flow rate, GPM. Okay, easy. But how do you convert the two piece into pump head? Anybody? Seriously? Nobody know how to do it? You really need to have more fluid class, especially with me. Okay. Okay, if you don't know, you can easily write down the Bernoulli equation between 1.1 and 0.2. Let's see how it goes. Because in the Bernoulli equation between 1 and 2, the pump head HP is there. Okay, HP should be equal to something related to the pressure. Okay, Bernoulli between 1 and 2. Okay, P1 over gamma plus Z1 plus V1 square over 2G plus pump head equals I assume you guys know how to do it. If you don't know, you really need to learn this. Okay, plus Z2 plus V2 square over 2G, no loss. Okay, immediately before, immediate after that, no pipe. Okay, it's basically no loss. Everybody agree? Is that what it is, right? Okay, I can write down the equation before I know what its answer is, right? Doesn't matter. I need to write down the equation first. So what does the HP equals in this equation? Anything zero? Or anything can be canceled? I think nothing's zero there, but a lot of things can be canceled.
Z's.
Yeah, Z actually are zero. They are on the datum, right? But they are also same. So before and after the pump is same, right? So they're canceled. Anything else? Anything
Would
else?
the velocities cancel because of conservation of mass?
Exactly. That means you paid attention when I previous talk, right? Previously, I just talk about suction and discharge. They have the same flow rate, conservation mass. No matter what velocity, they are the same. Okay, is that right? Remember this. These are the fundamentals you probably need to be very familiar with. So what the HP equals?
P2 minus P1.
It's not P2 minus P1. It's P2 minus P1 divided by
Gamma.
gamma. Gamma is the specific weight, right? 9,800 for water, right? Rho G, basically. So this is the conversion. That's why we only needed 2 pressure gauges. That's it. That's all we need to calculate the pump head. Okay, that makes sense? Right? That's why we need. Just read the pressure readings, okay? Divided by 9,800 for water, gamma. Then that's your pump head. So at any given flow rate, on any given flow rate, you should getting a pump head on any given flow rate. Let's say, hey, the flow meter here shows that's running like 100 GPM. 100 GPM, okay? Then the pressure P1, P2, you get some reading here, divided by gamma, okay, that's the HP. So you get 1 point joule on the pump curve. Okay, so you can have some different points joule on the pump curve. Then you can make a pump curve. Is that right? But how to make different points, different flow rates? Okay, so in that sense, doing measurement of the pump curve, you need many sample readings. Okay, and you need to at least the 5, 6, 7 different flow rates. So you need to control the flow speed, the flow rate in the piping system. Okay, so how do we control? So every time you change a flow rate, you will have different pressure readings. You can have different HP calculated. Then you can have another point, another point, another point. Then connect all those points together. They will be your pump curve. Is that right? Everybody understand this? Okay. So my question is, how do you change the flow rate? There are 2 options here. Okay, usually in the industry system like this, you have 2 options. One is there's always a valve on the piping system. You can always turn the valve on and off. Okay, close a little bit, open a little bit, then the flow rate can change, right? Is that right? Is that what we do? Another option is for the modern pump, you can always changing the RPM of the pump. Without changing the valve, then just changing the RPM of the pump. You can also change the pump speed. Then you will change the pump, change the flow rate in the pipe. Is that right? So what do? We we need to change the flow rate, right? We do the valve or we do the change the RPM? Or does it matter?
It'd be better to change the RPM, wouldn't it?
Yeah, he said change RPM. Do you agree? You want to change the valve instead? So what's the reason? You know, you're a future engineer. You say something, you probably want to provide, before you say it, you have some reason, you confirm justification in yourself, you know, make sure it's correct, right? So what is the reason you think it's changing the RPM? Or if you want to say
if you put a valve into the system you're introducing more loss and you're introducing another failure point. Because a valve can go bad.
No, let's assume valve will not go bad, but you said it will change the loss to the system. Okay, so but why you think change the loss to your system is not good? You see, here is the loss in the equation. The loss actually changes with velocity, but anyway, it changes. That's the system curve you want to measure. Oh, I'm sorry, the pump curve you want to measure, right? But anyway, that the loss also taking into effect in that. Well, why do you feel it changing the loss is a bad thing? So you want to change RPM basically, okay. Any other opinions? Okay, think about this. You're measuring the pump curve. So for a pump to operate on the different system, what does it perform, right? That's a goal for the pump. So you don't want to change the pump itself. You're measuring that particular pump when it runs at different systems.
So that would mean you would need a more powerful pump?
No. It's not more powerful pump. You have that pump. I want to measure the pump curve. I want to change the flow rate. Okay. So one option is changing the valve. There's a valve here. Let's say you have a valve here.
Wouldn't it be more like economical as well just to use the valve?
Why is it more economic? Okay, so I think let me say this. So the difference between the pump curve and the system curve is one is to measure the performance of the pump. One is to measure the performance of the system. Okay, so right now we are measuring the performance of pump. So you cannot change the pump basically. Okay, but what really the system curve means is, what does that mean? It means on the different flow rate, what different pump had. Basically it said, hey, this pump I put into the system in Cisco. Oh, I'm sorry, what's the company? Westlake, let's say, okay. I want this pump working in the Westlake system, okay. I want this pump working the other company, okay, the system. Then they will perform differently, okay. They will have a different flow rate, will have a different pump head. So that curve just tell you, okay, on a different system, okay, different flow rate, it will produce different pump head. Okay, maybe the pump working in my home, okay. I have a swimming pool, maybe I wanted to drive the flow, then it will work at this flow rate and this pump head. Okay, the idea is to measure the pump curve is you place your same pump into 7 different systems. Okay, record what the flow rate and what the pump head in different systems. And draw that curve. Okay, that makes sense. That's very important. Think about this. You bring your pump into different systems and what's the performance. Every system will have different performance, different Q and different HP. Okay, that's why you can draw the performance curve of that particular pump. Okay, in that sense, you don't want to change your pump. You change your system. So changing the valve that exactly serve the purpose of changing the system. You change the valve, the system loss changes a little bit. The whole system actually changes a little bit. Kyle, just like you say, hey, you change the loss, but that's exactly what we want. Okay, you don't want to change RPM. Basically, change the RPM, they serve as different pump. So you don't know what you're measuring actually. The first time I measure this pump, second time I change the RPM, I measure another pump. What the heck? What did I measure? Okay, so be careful, very, very careful on this. Otherwise it's totally wrong. Otherwise, when you change the RPM, basically you're measuring the system curve. Okay, because system, so you don't want to change the system, that's your system. Okay, so basically I have 7 different pumps. I put it into the system, 7 different pumps, I put it in the system. Every time I measure the flow rate, every time I measure the required pump head. Okay, so then this is the performance of that system. You don't change the system, you change the pump. Okay, so that's the difference. So when you change the RPM to control the flow rate, this is actually you're measuring a system curve. Okay, see the difference? Okay, very, very important on this. Otherwise, you do something opposite, basically. Okay, system curve means what system required the power. Okay, so you don't want to change your system. If you change the system, change the valve, you change your system every time. Okay, so I think that's the difficult part on the measurement, how to measure the pump curve and how to measure the system curve. Okay, so any set the RPM, that means a particular pump. Okay, if you change the RPM, you change another pump. So if you want to measure the pump curve, you set an RPM, never change. And you change the valve of the pipe, then you change the flow rate, then you will get the curve like this. Okay, vice versa, if you want a system curve, then you keep changing your RPM. Basically, every time you change your RPM, it means you replace a new pump into the system. Let's see how the pump goes. Okay, so that shows the performance of the system. Okay, so these are the fundamentals of the 2 curves. Any questions before I continue? Then one of the lab you will measure the pump curve, okay, in a pumping system. You measure the pump curve, then you measure the system curve, then there will be an operating point, okay, between for the pump and this system, okay. And also in that lab, that's not the next lab, but that will be in the system curve lab. You will need to use the equation in the previous page, this is system equation, to calculate your theoretical system curve. Okay, then compare to your measured system curve. Okay. Again, how do you measure system curve? Think about it. You are changing the RPM for changing the flow rate. Okay, again, still read the delta P. Okay, every point is the delta P. That indication, that the delta P between P1 and P2, it's to use to calculate your pump head, particular pump head at that moment. Okay, and versus different flow rate, you should be able to draw the system curve, measure the system curve. Then with that Bernoulli equation, you should be able to calculate your theoretical system curve. I want you to compare. Okay. Now, pump. Okay, you have one pump. You have a one pump curve like this. What about you put 2 pumps together? You know, in industry, really, you often see 2 pumps or 3 pumps work together, pumping parallel, pumping series. Okay, so if that happens, what is the resultant performance curve for pumping parallel or pumping series? Okay, that's my question. So let me share my screen. Okay, share my screen to another. Okay. Let me see. Did I open? Let me open the file, then share. Okay. How do I open? Oh, okay. I see how we do it. We can open it in here in my whiteboard. Here we go. Okay. Let me see. Let me share my screen here. Okay, there's one page here. Let me make it bigger. Okay, that I will give you the handout later. Okay, but this show the configuration for two pumps together. Okay, the top one is pumping series. Okay, the bottom one is pumping parallel. When they work together, okay, so look at the curves, performance curve in the right side. Okay, this pump curve A, for example, let's look at the pumping series first. The A curve is a single pump curve. Okay, single pump curve. So when you work together, two pumps, B is the pumping series, the resultant curve. So if the two pumps are the same, so on every flow rate, you're just adding the pump head between the two pumps together to become the pump head. Okay, so the resultant pumping series curve is very easy to make. If you have a single pump curve, it's doubled in the vertically. Okay, so when it runs at a flow rate, the pump head will be doubled. This is the pumping series. Okay, but the question is that really happens in reality? Your pump head doubled. Anybody? Do you think it would double or less than double or even less?
Be less than double.
It will less than double. What is the reason?
Because the pump can only add so much energy to the flow.
Okay, so try to learn using the system curve idea to explain it. Did you change your system? You changed probably slightly, but mostly your system doesn't change. Your system is just there. You still have the same system curve. Okay, so now look at the intersection between the system curve and the pumping, just one pump, it's here. So if you put two pumps together in series, actually your operating point is here. See, that's how you predict what is the performance, what is the flow rate in the pump head when you put two pumps together. It's not doubled, nothing doubled here. The flow rate even changed. See, for this particular system, when you put the pumping series together, actually the flow rate increased from here to here. And your pump head also increased from here to here. It's not simple to say, hey, the pumping series will double the head or keep the same flow rate. No, both changed. Is this against your intuition? Against your knowledge? Okay, be careful. Although when you draw the pumping series resultant curve, what you do is you double the pump head at every flow rate, but that's just for drawing the performance curve of the pumping series. In reality, it only works on one point on the curve, right? For that particular system. So for the same system here, if you put a single pump, it works here, work at here. If you put two pumps together, it works at here. Okay. Very important, very important, okay? So now you are an engineer, you can really help with the pump situation over there, okay? So now look at the pumping parallel. When you draw the performance curve of pumping parallel, basically for each pump head, you double the flow rate. So this is the resultant parallel curve, the B. Okay, you can produce it. You can predict it based on a single pump curve A. Okay, but then look at they put the system curve already in this figure. Now, if you place this single pump in your system, or if you place your pumping parallel in your system, it works at these 2 points. It gives you that much flow rate, and it gives you that much flow rate in the head when you do pumping parallel. Okay, again, nothing doubles or nothing unchanged. Likely everything will change if you run it at pumping series and pumping parallel. But which one's better? You don't know. Okay, which layout situation, which layout is the optimal choice? You don't know until you put it down together. For example, in this case. So before you have two pumps now, right? You try to decide, I want to put it into parallel or I want to put it in the series for my system. Okay, so you don't know. Okay, so what you do is let's compare. Let's compare. So here I have a single pump A. Okay, let's make the pumping parallel curve here. Let's also make the pumping series curve here. Let's say C. C is a pumping series. B is a pumping parallel. Okay. I think I made a wrong drawing here, but it's okay. You understand. Let's extend it a little bit. All right. Bear with my drawing. This is single pump. This is pumping series. This is pumping parallel. B is pumping parallel. C is pumping series. So which one's better? Series or parallel? Now you ask better in terms of what? Let's say better in terms of the both flow rate and the pump head.
Series.
Series you work at here. That's your operating point for the series. See, this is your system curve. You place your system curve on the pumping series and on the pumping parallel. You have two operating points. Okay. So which one's better? Let's say in terms of the flow rate and the pump head. Bigger the better, let's say. Which layout give you more flow rate? Is parallel give you more or series give you more flow rate?
Parallel gives more flow rate, but series gives higher pressure head.
Why? This is series. This is a parallel. Which one has a higher pressure head? Pump head?
Oh. So it would be parallel.
Is that right, everybody? You never deal with the pump stuff before in your life. Now it's time. It's very important. You have to look at the curves.
Confused by your graph.
What'd you say?
Can you explain that again? I'm kind of confused by the graph.
So which one you're confused about? Tell me exactly, specifically.
The one that you just recently drew.
C?
Yes.
C is this curve, just the pumping series curve. Okay. Do you know A? A is the original single pump curve manufacturer will provide to you.
So the only values that matter are the ones that actually intersect the system curve.
Exactly. That's why it's called operating point. See, the name tells, right? Operating point. So the pump will operate at this flow rate and this pump head. Okay. So again, let me repeat here. A is the single pump curve. Okay. Based on the theory, we know how to produce the pumping series curve. Basically, just for each flow rate, you double the pump head. Each flow rate, you double the pump head. Then you can produce the curve C, which is the pumping series curve. Kathleen, is that good?
Yes, sir. Thank you.
Okay, so this is the resultant curve for pumping series. And this one, B, you see the B? B is the resultant curve of pumping parallel. Okay, so you have two situations. Before you actually install this two pumps, you want to go run this. Okay, let's see how it goes. If I put a pumping series, this is the curve. If I put in pumping parallel, this is the curve. Now, I place my system on it. This is my system curve. So you have two intersections. One is the system intersect with the pumping series. One is the system curve intersect with pumping parallel. That two intersection tell you, okay, that's my future result. Okay, if I put a pumping series, it will work at this flow rate, this pump head. If I put a pumping parallel, it will give me this flow rate and this pump head. Okay, so which one give you greater pump head?
Parallel.
Of course, parallel, right? This is the pump head axis, vertical axis, a higher here. These are the two pump head, one for pumping series, one for pumping parallel. And these are the flow rate. Okay, horizontal axis is the flow rate. So this is the flow rate for pumping series, and this is the flow rate for pumping parallel. So in this situation, in your system here, if you put into parallel configuration, it gives you more flow rate as well as give you more pump head, which is, I think, is preferable. Okay, but not necessarily always. It could be in a situation that series will give you better situation. For example, let's say for this, I'm adding pumping parallel here. Okay, this is series. Okay, this is my system. Now I see I have this point and this point. It seems like in series give me higher pump head and a higher flow rate. Okay. It really, you see, if a non-engineer will ask a question like, oh, what should I do? Is pumping parallel better than pumping series? The answer is, I don't know. It depends on my system. Okay. If my system is a certain situation, there could be one is better than the other. Okay. It's not, unless I know my system, I cannot answer the question, which one's better. Okay. Does that make sense to everybody? Okay, that's really important knowledge here today I covered here. I hope you, if you're not fully understand, watch the video again. Okay, so it's really important for you. Okay, for the fluid topic, fluid task in if you work in the industry here, pump is very, very important. Okay, and this is basically that's the fundamental for doing pump selection, not only for single pump but also for the parallel and series configurations. Okay, so and you need to know the pump curve as well as the system curve before you can make a decision. Okay, so that's I will try to convey today. So for the detailed experiment, don't worry. Next week I will post the first experiment video. It will be a single pump measurement plus the pumping parallel measurement. Okay, so you will in the video I will talk about the detail, what you need to produce, what you need to measure, what you need to calculate. But today I just want to stop here just for covering the fundamental theories. Okay. For the details experiment, I will talk about it next week in the video. Okay. Any questions before we go? I'm a little bit longer than 1 hour today, so but I think it's so important, so that's why I like to spend a little bit more time. Okay. Any questions?
I have one question, Dr. Zhang.
Yeah, go ahead.
When we're comparing series and parallel pumps,
Mhm.
I mean, what determines which is more efficient? I mean, you're looking
No,
for
it won't determine which one is more efficient. It just
which
only
one is
can
better,
tell,
which one's a better choice.
it's
What
only
determines-
can tell you, it's not even appropriate for me to say a better choice. It even can just tell you which one give you a larger flow rate, which one give you a larger pump head.
Got it.
Okay, efficiency or not, then you need to look at the BEP, best efficiency range. Okay, there's some correlation for single pump BEP and the double pump BEP. So you have to find it, and then it's really a different story here. But here we can tell which one could give you larger flow rate and a larger pump head. Okay, which is a very important information for the design, right? You need to know what you need to predict before you actually put in the pump. What will be the flow rate? You know, I put two pumps together. What do I expect? So that's for the purpose. Okay. Good. Okay, so that's it for today. Have a nice rest of the day, you know, and I will post this class video online. And if you have still question or not sure, I think encourage you to watch the video again, and then you can directly communicate with me if you have other questions. Okay, I will post so this week is off week. You don't have a lab report to do. You don't have a lab to do. So next week, class time, I will post lab number 4. Okay. Okay, good. See you later.
Thank you.
You're welcome.